The Compton Effect. We mentioned Arthur Compton before, and so we return to him now. In 1923, he scattered X-rays off a graphite surface and observed that the wavelength of the scattered X-rays increased. That is, their frequency decreased. This was called the Compton shift. Compton postulated that the photon, acting as a particle with an energy E equals hf, collided elastically with an electron. Since momentum and kinetic energy are conserved in an elastic collision, the scattered photon would have less energy after the collision, some of that energy having been transferred to the electron. This would be observed as the scattered photon having a longer wavelength than the incident photon. To derive the equation for how much the photon's wavelength is shifted, Einstein's equation for the relativistic energy of a particle is used so that the momentum can be assigned to the photon. Einstein's relationship between energy and momentum was given by E squared equals P squared C squared plus M squared C fourth, where M is the mass of a particle, P is its momentum, C is the speed of light in a vacuum. But since the mass of a photon is zero, this becomes very simple. E equals PC. So the momentum of a light particle is given by E over C, or HF over C, or H over lambda. This equation shows that a massless particle, a photon, still has a momentum. After solving the conservation of energy and momentum equations using relativistic versions as photons move at the speed of light, the following angular dependent equation was derived, and it shows how much the photon's wavelength is shifted when it collides with an electron. So you're not really being asked to rederive this, but merely look at what it says. That the change in wavelength, the difference between the final and initial wavelengths of the photon, is given by h over mec times 1 minus cosine of theta. H is Planck's constant, m sub e is the electron mass, c is the speed of light, and theta is the scattering angle for the photon.